Okay, let's continue with some problems related to differential calculus. Question number one. In this problem, we'll see some uh, uh, we'll see the linear maps. Show that any linear map. So when we have linear maps defined on R, we know that it is always continuous. We'll see that it is the same in higher dimensions as well. Show that any linear map T defined from E to F, where this E is actually an Rn and this is Rm between two Euclidean spaces. Spaces is continuous. Moreover, we'll see something about its differentiability as well. Continuous. Furthermore, we know that every linear transformation defined on finite dimensional spaces can be represented as some matrix. If A, Aij is the matrix representation, representation of the linear transformation T with respect to some basis of T, then we have the operator norm of T. Firstly, we'll show that this is continuous, and since it is continuous linear map, we can, this operator norm is well defined. Then we'll show that this operator norm has some upper bound. So yeah, summation over I, then summation over j mod aij. We'll see the limits of I and j. Then further show that this T is differentiable at all points and compute its derivative. Solution. So we'll do it part by part. Firstly, we'll show that this T is continuous. Now we have T from Rn to Rm is a linear map. This implies we have a matrix A, Aij. Can you tell me the dimension of this Aij, this matrix A?
M into N.
Yeah, this will be M cross N such that T at any point X is equal to the matrix multiplication A times X, where X is a vector in Rn. Okay. So, firstly, we claim that this T is continuous. That is, for any epsilon positive, there exists a delta positive such that the norm Tx minus Tx naught is less than epsilon whenever norm x minus x naught is less than delta. Now Tx and Tx naught are in Rm, so I'll write it as M norm, and this x is in Rn, so I'll take x norm x minus x naught there. Okay, so that's what we need to show. So firstly, let's start with how our Tx minus Tx naught will look like. This is just matrix multiplication. This is Ax minus Ax naught, which is A1 plus A2, A1 n, A2 1, A2 2, A2 n up to An1, An n2, and so on up to An n times, this is m cross n. This will be x1, x2 up to xn. This is n cross 1 minus the same matrix, and here it will be. So I take x naught to be x naught 1, x naught 2, x naught n. This is n cross n, n cross 1. So this is equal to, you know, uh, how to multiply the matrices. So this will be summation j from 1 to n a1j times xj. Then we'll have the second, in the second row, summation j from 1 to n a2j xj, and so on up to summation j from 1 to n amj xj. Similarly, the second vector will be summation j from 1 to n a1j x naught j, summation j from 1 to n a2j x naught j, so on up to summation j from 1 to n a mj x naught j. So this is a vector tx minus tx naught. This is a vector which is equal to summation j from 1 to n. I can take a1j common. This is xj minus x naught j. Summation j from 1 to n a2j xj minus x naught j, and so on up to summation j from 1 to n amj xj minus x naught j. Next, we need to find the norm of this tx minus tx naught. Yeah, this is a vector in Rm. This is m cross 1 vector. So we know how we define the Euclidean norm. Tx minus tx naught m. Let's take it square. So it is summation I from 1 to m, and then we take square of the terms. So each term is summation j from 1 to n a ij xj minus x naught j whole square. Is it clear how we are taking this norm?
Yes, ma'am. This matrix is considered to be an element of R to the power n is m square, no?
Matrix is m cross n matrix, so not n square, it is rmn,
Oh, oh.
because we have mn terms. Huh? So right now I'm using it as a matrix only. So this is a vector, this is a vector, and its first term is a this whole summation. So I'm taking square of that term and eventually adding all these terms. So this is how we define our norm. This is the basic Euclidean norm. Now suppose this was B1, this was B2. So this was actually the vector B1, B2, Bm, and our norm, we know that this is summation I from 1 to m bi square. So yeah, in this each of bi, again we have summation. That's why we are getting this two summations. Next, we'll use the Cauchy-Schwarz inequality. So from here, I'm saying that this is less than equal to summation I from 1 to m as it is. Inside, I'm replacing it by summation j from 1 to n aij square times summation j from 1 to n xj minus x naught j square. Why? Because by Cauchy-Schwarz inequality, we have summation I from 1 to n. So we have something of this form. This is less than equal to, this is the inner product. This will be less than equal to the norm. ai square to the power 1 by 2 summation I from 1 to n bi square to the power 1 by 2. And taking ai to be aij and bi to be, then we take ai to be aij and bi to be xj minus x naught j. So from there we get summation I from 1 to n aij times xj minus x naught j. This is less than equal to summation I, I, I from 1 to n. We have summation j, na? So it's better to take j. J from 1 to n. J from 1 to n. aij square to the power 1 by 2 summation j from 1 to n xj minus x naught j square to the power 1 by 2. Now squaring both the sides, we get summation j from 1 to n aij xj minus x naught j to the power 2. This is less than equal to, yeah, because we had whole square. This is less than equal to summation j from 1 to n aij square times summation j from 1 to n xj minus x naught j. Yeah, that's how we get this inequality. And now since this term is independent of I can take it outside the summation. So this will be equal to summation j from 1 to n xj minus x naught j times This is summation I from 1 to m, summation j from 1 to n, aij square. So if I, now since this is constant, it does not depend on x in any way. So I can take this as, suppose alpha is equal to summation. This is just the sum of all the terms after taking square in the matrix. So this will be a constant. Then this implies dx minus dx naught m square. This is less than equal to alpha times summation j from 1 to n xj minus x naught j square. Now this term is the Euclidean norm square. This is equal to alpha norm x minus x naught n square. Now this will be less than alpha times delta whenever the norm delta square x minus x naught n is less than delta. Taking delta to be epsilon by root alpha, we get norm dx minus dx naught m square. This is less than epsilon whenever epsilon square whenever norm x minus x naught n is strictly less than delta. Now this is what we wanted. This gives us the definition of continuity. This implies for any epsilon positive, there exists delta which is equal to epsilon upon root alpha, obviously but depending only on epsilon, such that norm dx minus dx naught m, this is strictly less than epsilon whenever norm x minus x naught n is less than delta. Therefore, T is continuous at x naught, and since x naught belonging to Rn is arbitrary, we get T is continuous on whole Rn. We have defined it on record. So please go through this proof of continuity, how we have used the Cauchy-Schwarz inequality. And if you have any doubt, please let me know. The main idea was to use the Cauchy-Schwarz inequality.
Ma'am, the value of alpha should be strictly greater than zero, no?
Yeah, it will be. No, it need not be positive. Yeah, because this is square, no? Okay, this is square. So this will be positive. Yeah, only if T is a non-zero linear transformation. If T is zero linear map, then all Aij's will be zero, and hence that will be zero. But yeah, in that case, we should have said that if T is a zero map, then it is clearly continuous. We did not do anything. And if T is non-zero, then we can do all these things. Yeah. Okay, so next we'll look at the operator norm. Now, since this T is a continuous linear map, therefore it is a bounded linear operator, bounded linear function. It's T is linear and continuous. This implies t is a bounded linear function, and we can talk about its operator. So we'll show that its operator norm depends somehow on the terms of the matrix. The operator norm of T is less than equal to summation I from 1 to m, j from 1 to n. So we know that by definition, the operator norm, this is equal to supremum of norm Tx. Now this Tx is in Rm. So now x, which is in n, for every x in Rn minus 0. Now we need to look for upper bound of these terms. So again, as we were doing earlier, we'll see first how this dx will look like. The terms of dx, this is again a times x, which is a vector of the form summation j from 1 to n, a 1j xj, and so on up to summation j from 1 to n, a mj xj. This is an m plus 1 matrix. So its Euclidean norm will be, let's take it square. This will be summation I from 1 to m, then summation j from 1 to n, aij xj square. Then again, we'll use the Cauchy squares. Or yeah, let's take this norm x as well. And norm x n square, this will be summation j from 1 to n xj square. So this implies norm dx m square by norm x n square. This is equal to summation I from 1 to m, j from 1 to n, aij xj square upon summation j from 1 to n xj square. Next, we'll use the Cauchy-Schwarz inequality on the numerator. So this will be less than equal to summation I from 1 to m as it is. Inside, we'll use the Cauchy-Schwarz. This will give us summation j from 1 to n aij square times summation j from 1 to n xj square on summation j from 1 to n xj square. Now this term, this is independent of I, so I can take it outside the summation. So this will be equal to summation j from 1 to n xj square times summation I from 1 to n summation j from 1 to n aij square on summation j from 1 to n xj square. These two will get cancelled out. So we are left with summation I from 1 to n j from 1 to n aij square. So taking square root on both the sides, we'll get norm Tx upon norm x will be less than equal to summation I from 1 to m, j from 1 to n, aij square to the power 1 by 2. So can you tell me how can I go from here to what we want? We want this to be lesser than equal to. So I want this power half to come inside and it should become something like this. So can you tell me how we can do this?
Ma'am, is it Minkowski inequality?
Hmm, Minkowski. Yeah, in Minkowski, we eventually get power inside, no? Or otherwise, you can see that. I just wanted you to see that this is actually something like uh, sum of squares of some terms, some number of terms. Suppose mn square, then its power half. Now we know that this term is always less than equal to mod b1 square, b2 square, sorry, even bmn whole square to the power 1 by 2. Because we know when we use the binomial expansion, this term, the square will have terms of this form plus some positive terms. So eventually, this side will be the greater one. So that's what I wanted you to think about. Yeah, eventually that's the same inequality. So this will be now we can cancel these powers. So this will be mod b1 plus b2 bn. So yeah, that's what we are using here. Yeah, we get summation I from 1 to m, j from 1 to n, mod h. So that's what we wanted to show. Now, since each term is lesser than equal to this, so the supremum will also be less than. Therefore, the operator norm will be less than this term.
Ma'am,
Hmm?
how this definition of operator norm using supremum is equivalent to that of infimum we had seen earlier.
So this supremum is equal to?
Actually, we had seen that operator norm is equal to infimum of all positive c such that norm of
Yeah,
tx is less than equal to.
these both definitions are equivalent. I think it was some exercise problem. No?
Yes, ma'am.
So did you look for the solution for that problem? I mean, did you
Sorry,
search?
ma'am.
It's okay, it's okay. I'm just asking. Okay, then I'll give you a proper proof. And that Minkowski inequality is something else. Even I got confused. Minkowski inequality is for sum. Is something like this summation k from 1 to n. It's k plus by k to the power p So it helps us to get the triangles inequality form. This was Minkowski inequality. I think that's something different. Yeah, here we can use this fact using the binomial expansion. So generally, whenever we are trying to find the operator norm, we have always used this definition. This is quite convenient because take finding alpha infimum of all those alpha positives such that that condition holds. That's a bit tricky task. So yeah, okay. If I remember in next class, I'll give you a formal proof for this. You can also look for it on Stack Exchange or somewhere on Google. You'll find it. Okay. So I hope this is fine. How we get this inequality? So this is happening for every x in Rn minus 0. So this implies supremum norm Tx by norm x in Rn minus 0. This will also be lesser than equal to summation I from 1 to m and j from 1 to n mod h. That's what our operator norm looks like. So next we need to show the differentiability. So this is a linear transformation. We are when we are in higher dimension. So if we take dimension to be 1, in that case, how does our linear maps look like? Our linear maps are, suppose I say T from R to R is a linear map, then that means it is something of the form ax plus b. So in that case, our derivative p dash x is equal to a for every x. So this gives us an idea that a derivative is some constant for every x. So here also for higher dimensions also we'll get some constant kind of derivative. So let's see. Claim.
Ma'am,
Hmm,
this linear map is linear transformation or linear function?
that's the same.
You define Tx is equal to Ax plus B,
Hmm.
then
This
will
is
it be linear transformation?
no. This is not linear transformation. This is just a linear map because for that we need t of 0 is equal to 0. No?
Hmm.
This is just a linear map. But right now we are talking about yeah, there also we have just linear map, no? Linear transformation. Yeah, it should. I think it means this here the linear map means the linear transformation. Then only we can find the matrix. Huh? Otherwise, we'll have some ax plus b type of form. Yeah, consider it to be linear transformation. Yes, differentiable. So t is differentiable. That means the norm. That is, there exists a linear map. That is, there exists a linear map. Can call it something t bar, or let's write it as dt at x, such that tx plus h minus dx minus dt at h upon norm h, this norm should converge to 0. If we are able to find such a linear map, then we say that our function is differentiable, and this dt is called the derivative. So here, let's look for such a linear map. So if we consider tx plus h minus tx, so this will be,
dtx of h.
yeah, dtx. Dx at h. This can just to see. So this is a x1 plus h1 x m plus h. So x m no? M plus h n minus a x1 x2 up to xn. So after simplification, you'll get this to be summation j from 1 to n a I j, that will be x1 plus h1 minus x1. So eventually just h1 a1j. A1j. This will be summation j from 1 to n amj. And here we'll have hn. hm. This should be hj, no? Because we have, write it again. This is a11, a12, a1n, a21, a22, a2n up to am1, am2, amn times x1 plus h1, x2 plus h2, xn plus hn minus this will be summation a1j xj j from 1 to n, so on to j from 1 to n amj xj, and this will be summation j from 1 to n a1j times xj plus hj, yeah, minus summation j from 1 to n a1j xj, so on to summation j from 1 to n amj xj plus hj minus summation j from 1 to n amj xj. So this will be, you can take summation aij to be common. So this will be summation j from 1 to n a1j times hj, summation j from 1 to n amj hj. So which is a times the made vector h1 h2 hn, which is ah. So if I define, if I take the map to be this ah, that means if we take dtx to be the linear map t itself. So from there we'll get dtx at h will be t at h, which is a times h, and from above we have tx plus h minus tx minus ah. This is 0 because tx plus h minus tx is equal to ah. Now this ah can be replaced by tx at h. This is equal to 0. So the norm divided by norm and take the norm, then apply limit, then also it will be 0. Therefore, t is differentiable, and dt at any point x is equal to t for every x. Yeah, this you can see that in the case of one dimension. If we have a linear transformation, then that tx will be of the form ax, and its derivative it will always be equal to a. Here, this t is also same as the matrix A. So yeah, that's how we can see this in one dimension. Therefore, our function is differentiable and its derivative is constant. So I hope this is fine how we prove that linear maps are continuous. Then we have an upper bound for that for the operator norm of the linear map. And then we have seen that this linear map T is differentiable and its derivative is constant. Okay, so let's look for some nonlinear functions and their derivative. So yeah, this is an example. So f is a function from R2 to R2 where fxy, this is equal to xy comma x square minus y square. So all we need, I need you to look again is the fact that the Jacobian matrix is always the best approximation for derivative because it is very difficult to assume what derivative we should take because there is no specific way in which we can find the derivative. We need to find such some linear map which satisfies this condition. So a good idea is to start with the Jacobian. So how we define Jacobian for some function f. So jf, this is if our f is a vector function of this form, then jf is given by gradient f1, gradient f2, and so on up to gradient fn. So in this case, can you find the Jacobian? Yeah. Jf at xy is equal to
Matrix of uh, first column y2x and second column x minus 2y.
here our f1 xy is xy and f2 xy is x square minus y square. So we'll show that the linear map corresponding to this matrix will give us the derivative. That means uh, claim that limit h tending to 0, or instead I'll write h comma k because we are in R2, k tending to 0, 0. The norm f x plus h y plus k. So that's f of x plus h minus f x comma y minus gf x y at h times the vector h comma k upon. So in R2, our norm is the Euclidean norm, h square plus k square. This converges to 0. I think you can evaluate this. F x plus h y plus k minus fxy. I'll write in the form of vector. So this is x plus h y plus k minus xy. And then we have x plus h square minus y plus k square minus x square plus y square, which will be this will be just kh, because this xy term will be cancelled out. So kx plus hy plus hk, and here also we'll have h square plus 2xh minus y square minus 2yk. Then gfxy times hk, this is the matrix yx 2x minus 2y times hk. So this will be again a vector hy plus xk 2xh minus 2yk. From here we get fx plus h y plus k minus fxy minus Jacobian fxy times hk. This will be kx plus hy plus hk minus hy minus xk. From here, then the second term will be h square plus 2xh minus y square minus 2yk minus 2xh minus 2yk. It should be plus 2yk, no? Same thing. From here, hy, xk. It's cancelled out. Denominator, I should be left with h square minus k square. Yeah, here. This should be k square. This is 2xh, 2xh, 2yk, and this is plus 2 because we are taking negative of gfxy. No? So 2yk gets cancelled out. This is hk and h square minus k square. So next we need to see its norm. So let's take its square. So this square, this will be hk square on under h square plus k square. That's also square by h square plus k square minus this will be plus h square minus k square by h square plus k square. I want this to converge to 0 as h comma k goes to 0. L1 be limit h comma k tending to 0, 0, hk square by h square plus k square, and L2 is limit h comma k going to 0, 0, h square minus k square h square plus k square. So can you evaluate these limits? Yeah.
By putting h to be r cos theta and k to be r sin theta,
Mhm. So we'll
I
have
think
r to the r square cos theta sin theta, mhm, r to the power 4. Huh? And the denominator will be,
r square. As r tends to 0, it will equal to 0.
so we are taking h is equal to r cos theta and k is equal to r sin theta. So from here, can you say anything? Because we don't know about theta, na?
Oh, yes.
So instead, you can do one thing, this h square k square upon h square plus k square. This is less than equal to. Now this h square itself is lesser than equal to h square plus k square, and k square is also lesser than equal to h square plus k square. So this gets cancelled out. Now everything is in numerator and we know that h and k are going to 0. So this will go to 0 as h comma k goes to 0 comma 0. So yeah, I can take modulus as well. So eventually this will converge to 0. And for L2, this is equal to h square upon h square plus k square minus k square upon h square plus k square, limit. So we can evaluate the limits separately. Again here, h square plus h square plus k square, this will be less than equal to. Oh, I need to take square also, no? In L2 norm, we need to take square of each terms. So I cannot take this separately. So instead, yeah, we can just use the expansion. This is limit h comma k into 0, 0, h power 4 upon h square plus k square plus k power 4 upon h square plus k square minus 2h square k square upon h square plus k square. So this will go to 0 as we did earlier in the case of L1. And for these two, again, we can write h power 4 h square plus k square. This is less than equal to h square plus k square whole square upon h square plus k square, which is h square plus k square, which goes to 0 as h and k goes to 0. Similarly for k power 4. So therefore, both the limits L1 and L2 are going to 0. That means limit h comma k going to 0 comma 0. This was, yeah, fx plus h. So norm of f x plus h y plus k minus fxy minus j fxy times hk L2 norm on the L2 norm of HK, this goes to 0. That's what we need to show when we need to show that the function f is differentiable and its derivative is given by this function. So yeah, in this case, again, we were able to find the derivative, and the derivative was evaluated using the Jacobian matrix. That was actually the Jacobian matrix. So I hope this is clear how the Jacobian gives us the derivative. So while searching for derivative, we can at least start with the Jacobian. So that gives us some direction. At least we have some direction. Next question. Consider therefore f is differentiable and dfxy is equal to jfx. Consider the set of all n cross n square matrices. We can identify this set as Rn square because eventually again it is a matrix has n square terms. So we can write it as a tuple. So we can identify this set with the set Rn square. Hence, the n cross n matrix becomes a normed vector space. Prove that norm AB, where AB is the normal matrix multiplication, this is less than equal to norm A, norm B. Again, this is just a bit of calculation. So when we have matrix A, Aij, n cross n, and B, Bij, n cross n, we know A times B. Let's write it completely. A11, A12, A1N, AN1, AN2, ANN times B11, B12, B1N, BN1, BN2, BNN. So if AB is equal to Cij n cross n, then we know that the Cij is given by summation Ai. We take ith row of A and jth column of B. So this is BKJ. K from 1 to n. So that's how we find, we multiply two matrices. Then, yeah, now we need to find the norm on the vector, on the matrix. So vector AB in Rn square. So this implies AB n square square. This is equal to, so we need to take sum over I as well as j Cij square. And we know that our Cij is given by summation k from 1 to n aik bkj. And we take square of this. Again, we'll use the Cauchy squads. So this is less than equal to summation I from 1 to n, j from 1 to n. Inside we have k from 1 to n, aik square times summation k from 1 to n, bkj square. Now this term is independent of j and this term is independent of I. So we can write this as summation I from 1 to n, k from 1 to n, aik square times summation j from 1 to n, k from 1 to n, bkj square. Now here we can replace this term k by j and here k by I. So this is basically the norm of a square because eventually we are taking sum of square of all the terms, then times b square, 4 n square. No? So yeah, everywhere this is small n, capital N, and rest up. So this is capital N cross n cross n, n, n. So yeah, everywhere it should be uniform. You can take either small n or capital N. Yes, square, square, and square. Taking square root both the sides, we get norm AB is less than equal to norm A, norm B. So yeah, you were asking some doubt related to the example after this, no? This class.
Yes, ma'am.
What was your doubt? Because that's a big example. I was saying that.
Yes, I think that example uh, is to find the inverse of a map from a open set U of subset of M and R to M and R. We
So they
send
are.
the matrix A to A inverse.
Hmm.
So actually, there is a claim improving in finding the differentiation of that map,
Which
and
claim?
then we claim that if norm of I minus M is less than one
Hmm.
operator norm, then M is invertible.
Yes. So you are not able to prove this claim.
Actually, sir had proof. Yes, yes, I don't understand this proof. And then
Okay.
further,
Hmm.
sir, find the differentiation of this map. And that process we don't understand how
The
we find.
derivative part is a bit bigger one, but I can explain this part. So we claim that I'll write it somewhere. Claim that if the operator norm of I minus M, this is less than 1, then M is invertible. So this is intuitive as a linear transformation can be. Mm. So here they are saying that if Suppose M is not invertible. Suppose M is not invertible. Now, what is this M? This M is a linear transformation, no? M is a linear
Yes,
map.
M
So
is a
that
matrix means linear matrix.
matrix means linear map, and when it is not invertible, that means we can find some non-zero vector such that it is mapped to 0. That means our kernel is non-empty.
Oh,
Our kernel is not singleton 0. So from here, this will imply that norm IV minus MV upon norm V, this will be just 1, because I identity IV is V, because identity maps V to V. M is mapping V to 0, and on denominator also we have V, so this is 1. So this implies the operator norm of I minus M, operator norm which is supremum norm IV minus MV upon norm V, uh, for V non-zero. We are given this is strictly less than 1. If this is strictly less than 1, that means norm IV minus MV should be strictly less than 1 for every V non-zero, because obviously this term will be lesser than equal to its supremum. So from here we are getting contradiction. But if I say this as V naught, but I V naught minus M V naught upon norm V naught, this is equal to 1, which gives us the contradiction. Therefore, this M should be invertible. Further, they are trying to find the derivative using this is kind of expansion. No? This
yes,
kind of
ma'am. And one
expansion.
thing also, yes,
Mhm.
sir, in his lecture, he told that if A is invertible, then we can find a small ball around A consisting of only invertible matrices.
Yes, because initially we have shown that this set of all invertible matrices is an open set. We
Oh,
started.
GLNR is open. Okay, okay.
Yes, yes. We have used that fact that it is open. Therefore, you can find an open ball. Basically, we are saying that. So that means we can find some ball where the elements inside it will be eventually invertible. That's what they are using. Okay, let's move to next problem then. Next we have bilinear map. So that any bilinear map between Euclidean spaces is automatically continuous. And that any bilinear map between Euclidean spaces is is continuous. Let's write it out. Is continuous. Yeah, where the metric on the product is anyone with the characteristic property. Basically, we have a metric on the product space also. So basically, we'll use the fact that bilinear maps are we have bilinear maps are defined from E cross F. That means we need two matrix spaces to G, and such that they are linear with respect to one variable. That means if I fixed the first component, suppose x, and take the second component as variable, now this is a function in one variable. This is linear. Similarly, b dot comma y this is linear, then we say that our B is a bilinear map. That means it is linear with corresponding to each component. Bilinear. So again, then we'll be using the fact that we have seen earlier that the linear maps are continuous, and hence our bilinear function will eventually be continuous. Let's prove that properly. Consider the bilinear map B from E cross F to G. We claim that this B is continuous. That is, for any epsilon positive, there exists a delta positive such that bxy minus bx naught y naught. Now this norm is the norm of G, strictly less than epsilon whenever x y minus x naught y naught. This is less than delta. And here we have norm of E cross F. So we have bxy minus bx naught y naught. We can just add and subtract bxy naught. So this is bxy minus bxy naught plus bxy naught minus bx. So this is just bxy minus y naught plus bx minus x naught y naught. Now since if I denote b1, let's take b1 to be define b1 at any point, say z. This is equal to bx comma z. For every z in, the second component is in f and b2. So in b1 we have fixed the first component, and b2, this is equal to b z comma y for y naught, because we need that for every z in B. Now since B is a bilinear map, this implies B1 and B2 are linear maps. Linear maps. Obviously this B1 is from F to G and B2 is from E to G. Again, since they are a linear map, hence continuous. Hence continuous. So this implies for above, for any epsilon positive, they can find delta 1 positive such that mod b1 y minus b1 y naught, this is less than epsilon by 2 whenever norm y minus y naught, this is less than delta 1. And yeah, I'll write it here only, delta 1 and delta 2 positive such that b2, this is norm of G, b2 in x, b2 x minus b2 x naught, G, this is less than epsilon by 2 whenever norm x minus x naught, this is less than delta 2. Taking delta to be minimum of delta 1 and delta 2, we get norm. So I can write b1y as bx comma y minus bx comma y naught. This is less than epsilon by 2, and b x comma y naught minus bx naught comma y naught. This is less than epsilon by 2, and this is happening whenever norm y minus y naught is less than delta. Instead, I should take this. I need something. Delta and x minus x naught is again less than delta. So let's keep this in this way only. Let's make this as number 1. And this one complete as number 2. So by first and second, we have norm b xy minus b x naught y naught. This is less than equal to bxy minus bxy naught plus bxy naught minus bx naught y naught, which is less than epsilon by 2 plus epsilon by 2, whenever the maximum of y minus y naught x minus x naught, this is less than delta. Why did I take this? Because we know that on finite dimensional spaces, all norms are equivalent. So I can take this norm also, and this will be equivalent to the product norm. So from there we'll get xy minus x naught y naught e cross f. This will be less than delta. So from here we'll get bxy minus bx naught y naught g. This is strictly less than epsilon whenever xy minus x naught y naught, this is less than delta. Therefore, our bilinear map is continuous. I hope this is fine.
Yes, ma'am. Uh, can we see bilinear map to be a matrix form in matrix form?
Mhm. Yeah, if we fixed one of the variable. If you are fixing one of the variable, then it's a linear transformation. Then it's a matrix. I don't think we can do taking both the variables with as variables. Okay. So next we'll do some application of chain rule. Let f from U to F, where this U is a subset of Rm and this is equal to Rm. uh, be such that f is differentiable at x. Now fix some v in Rn. Define gamma 1 and gamma 2 maps from -1 comma 1 to u, which are differentiable. Yeah, instead of Rn, I think we should write here u, such that gamma 1 at 0 is equal to x, which is equal to gamma 2 at 0, and the derivative gamma 1 dash at 0, this is equal to v. Then show that f of gamma 1 prime at 0 is equal to f composed to gamma 2 dash at 0. You try it. I'll just come back in 2 minutes. Here all you need to use is the chain rule. It's just an application of chain rule. Try it. I'll just come in 2 minutes. Okay. So, yeah. We know that by chain rule solution f composition gamma 1 derivative at 0, this is equal to derivative of f at gamma 1 at 0. Now f dash is a linear map, f dash gamma 0. Now gamma 0 is an element in U. So f dash gamma 0 is a linear map and its value at gamma 1 dash 0, its composition with gamma 1 dash 0. Again gamma 1 dash 0, this is a map, gamma 1 dash at any point x will again be from some from minus 1 comma 1 to u, and u is a vector in Rn. Yeah. So this will be equal to f dash, or instead, yeah, gamma 1 0 is x, its value at gamma 1 dash 0. Gamma 1 dash 0 is v. So we can write it as df x at v. And similarly, f composed with gamma 2 dash 0, this is by chain rule. This is equal to f prime gamma 2 at 0 at gamma 1 prime at gamma 2 prime at 0. So this is again df at gamma 2 0 is again x. So df x at gamma 2 prime 0, which is v. Yeah, since these both the terms are same, so the derivative is also e. So if at some point two maps are same and their derivatives are also same, so eventually the composition, the derivative of the composition with some other function, some other differentiable function, that will also be same. That's the main idea. Next, we'll be proving the radial form of the Laplacian. Let f from R2 to R be C2 smooth. C2 smooth means all its partial derivatives up to second order are continuous, smooth. Then we define a function g from R2 to R as g at R comma theta. This is equal to f r cos theta. So basically we are converting f into its polar coordinates. We are taking x equals to r cos theta and y equals to r sin theta. Then show that d1 d1 f plus d2 d2 f, this is equal to d1 d1 g plus 1 by r square d2 d2 g plus 1 by r d1 g. That means now this d1 d1 g d1 d1 f is basically the partial derivative with respect to the first variable two times. So if I take that to be x, so this is del 2 f by del x square. This is del 2 square f by del y square. So which is basically the Laplacian of f. No? And here this is yeah, for g our variables are r theta. So this is del 2 g by del r square. Yeah, and this is del 2 g by del theta square. And this is del g by del r. Let's see solution. We are given that f has all its partial derivatives. So we start with again taking x to be r cos theta and y to be r sine theta. So d1g, which is del by del r of g. G is f r cos theta, r sine theta. So this is equal to, so instead I'll write it to be xy, where xy are as defined above. So this is del f by del x. Then we have del x by del r. From here, let me write it first. Del x by del r, this is equal to cos theta. Del x by del theta, this is equal to minus r sine theta. Del y by del r, this is equal to sine theta. Then del y by del theta, this is equal to r cos theta. So this is del f by del x times del x by del r plus del f by del y times del y by del r, which is cos theta del f by del x plus sin theta del f by del y. Next, we'll again differentiate it with respect to r. This is d1g. This is equal to del by del r of cos theta del f by del x plus sin theta del f by del y. Now, cos theta is independent of r. This can be taken outside. Then we need to differentiate this with respect to r. This is a function of x and y. So again, this will be del 2f. So instead, I should write del by del x of del f by del x by del r plus del by del y of del f by del x times del y by del r. Then again, sine theta is independent of r. This will be del by del x of del f by del y times del y by del r plus del by del y of del f by del x. Sorry, del f by del y, del y by del r, and this should be del x by del y. So basically, we are differentiating firstly with respect to x, and then we are differentiating x with respect to r. So we have dx by dr as cos theta. I'll write it here only. So this is cos theta. This is sine theta. This is again cos theta. And this is sine theta. So this becomes cos square theta times del 2f by del x square plus sine square theta times del 2f by del y plus 2 times sine theta cos theta del 2f by del x del. Since f is a smooth function, so del x del x both are same. Eventually we can add it. This is d1g. Let's mark this as number 1. Similarly, we'll evaluate d2g. d2g means differentiating with respect to theta 2 times. Similarly, get d2g is del by del theta of f xy. So that will be del f by del x, del x by del theta, plus del f by del y by del theta. So which will get minus r sine theta del f by del x plus r cos theta del f by del. And again, yeah, d to g, this one is number one, this one is two. Then we need d2g. That means del by del theta of minus r sine theta del f by del x plus r cos theta del f by del y. Now, this is also dependent on theta. This is also eventually depending on theta. So, this time we'll have to use the product rule. So, we need to be a bit careful about all the calculations. This is equal to, we can take r outside. So, sine theta as it is. Now, we'll differentiate this with respect to theta. So, firstly, with respect to x, then x with respect to theta, then with respect to y, then y with respect to theta. Then del f by del x as it is, derivative of sine theta is cos theta. Plus r, again cos theta as it is, del by del x of del f by del y, then derivative of x with respect to theta, plus respect to y, then derivative of y with respect to theta, plus del f by del y as it is, derivative of cos theta is minus sin theta. So now, this is equal to, since dx by d theta is dx by d theta is minus r sine theta. So I'll replace it here only, or let's write it again. So minus r sine theta dx by, so this is d2f by dx square, and then dx by d theta is minus r dx by d theta is minus r sine theta, minus r sine theta. Then we have plus sine theta times del 2 f. Okay, so this is del f by del x by del x del y. Del y by del theta is r cos theta plus plus del f by del x cos theta plus r times cos theta del 2f by del x del y. Del x by del theta is minus r sine theta plus del 2f by del y square. Del y by del theta is r cos theta minus sine theta del f by del y. So eventually, after dividing it by r square, you'll get d2 d2g by r square, because that's what we need to prove. We need 1 by r square d2 d2g. So this will be sine square theta, sine square theta del 2f by del x square plus cos square theta del 2f by del y square minus 2 cos theta sin theta. You just need to simplify the above terms. We'll get this minus 1 upon r cos theta del f by del x plus sin theta del f by del y. This term is equal to d1g by r by first cos theta del f by del x sin theta del f by del y. So this can be written as I can take this d1g upon r on the left hand side. We'll get d2 d2g by r square plus d1g by r. This is equal to sine square theta del 2f by del x square plus cos square theta del 2f by del y square minus 2 cos theta sin theta del 2f by del x del y. So eventually, what do we want? We want d1 d1g plus this term. So this implies by equation 2 d1 d1g plus d2 d2g by r square plus d1g by r. This is equal to now d1 d1g was we are going to know first, yeah, by equation 2. This is cos square theta del 2f by del x square cos square theta del 2f by del x square plus sin square theta del 2f by del y square. And we have one more formula plus 2 cos theta sin theta del 2f by del x del y. And rest of the terms, I'll mark this as third and second and third. This is plus sine square theta del 2f by del x square plus cos square theta del 2f by del y square plus 2 cos theta sin theta minus del 2f by del x del. Now these two terms gets cancelled out, and since sine square x plus cos square x is 1, yeah, so many calculations. No, I don't think we have any other method. If you can find then that would be great for me also. So yeah, this is just del 2f by del x square plus del 2f by del y square. That's what our d1 plus d2 d2f. That's what we had to prove. So I hope this is clear. Anyways, all this is just partial derivative. It seems calculative, but eventually the things that we had used is just the product rules. Yeah, product rule and the chain rule.
Ma'am, initially you named this problem a radial function something.
Yeah, we are actually converting this Laplacian in form of if we have radial function, suppose. So in Rn case also, so we can say that it is the radial form of the Laplacian. That's it. So from xy to r theta.
Theta Uh, uh, how this is radial? Here
Yeah,
F is radial or G is radial?
no, by radial we mean that we have converted our problem in the form of r theta, no?
Oh, polar form.
Yeah, polar form. So next we'll see that on connected domain. Our function is constant if and only if the derivative is zero. Let U be a subset of Rn be connected. This we already know in R that yeah, there also I think we proved this, na, that function is the derivative is zero if and only if the function is constant on the connected domain. So basically we use the mean value theorem. Did f
Yes,
for
ma'am.
u to f is differentiable. Show that. So I think I can leave that for you. You can do that yourself. Show that f is constant. So mainly you have to use the mean value theorem again. If and only if dfx is equal to 0. So if it is constant, then directly you can use the zero map solution. Suppose f is constant, in that case we have fx is equal to fx plus h. So if I take dfx to be the zero linear transformation, zero linear map, so we get fx plus h minus fx minus dfx at h upon norm h. This will be eventually be equal to 0. So yeah, then we can apply limit as well. This implies dfx is 0. Conversely, you can see that if dfx is 0, then by mean value theorem for any b and a, this will be less than equal to k times norm b minus a, where this k is only condition on this case that it is greater than equal to dfx, the operator norm. Now since the df is 0, this is 0, so I can take this k as small as I want. So eventually I'll end up getting fb equals to fe. Only if the domain is connected, then only I can take b and a near to each other. So yeah, I would like you to try this proof, writing this proof properly.
Okay, ma'am. Ma'am, what will be the problem if U is not connected?
Yeah, in R you can see now, if I define a function from 0, 1 to 2 to 3 to R, and fx is defined as, suppose this is equal to 1 when x is in 0 interval 0 to 1, and this is equal to 2 in 2 to 3. Here also the derivative will be 0 because it is constant in open interval 0 to 1. Here also it is constant, and here also it is constant, so the derivative will be 0, but the function overall is not a constant function. That's the main problem.
How derivative is zero? We see derivative in a distinct interval
Yes,
in
this is
overall
kind of
domain.
a splitwise function. Our domain is again union of two disconnected sets. This is how I'm taking my domain. My domain is not connected, na? So when we have
Yes, ma'am.
connected sets, so we can define two constants on the disconnected sets. Then also our derivative will be zero. Okay, so I'll stop here. In next class, we'll start with some Taylor expansion. Okay, next class will be maybe next to next week, most probably on Tuesday. You'll get notification regarding that.
Okay, ma'am.
Hmm?
I want to ask that the mean value theorem that we have seen in several variable
Hmm?
um, and mean value theorem in one variable.
Hmm?
So this mean value theorem in one variable is a special case of multivariable mean value theorem, isn't it?
Ideally,
Or
it should
they are,
be. It should be, no? Because we are kind of
yes.
generalizing it to higher dimension.
If you put m and n to be one
One,
in
yes,
higher
yes.
dimension, then
Then it
so
should be.
there is an assignment problem in which it is asked that proving of Clairaut's theorem uses mean value theorem of several variable. It is correct or not? So in proof of Clairaut's theorem, it uses mean value theorem of one variable. So
Okay.
if it use the one variable, then since it is a special case of multivariable mean value theorem,
Yes, yes,
so
yes.
can we
We
not
can
say?
use that. You can
Can we
use
not
that.
say that Clairaut's theorem use mean value theorem of several variable?
So I don't know the exact proof. Maybe if they are saying if they are using the mean value theorem for the for the higher dimension, and you
One
want,
variable.
yeah, you want to use this version for one variable.
Mm. Actually, in proof of Clairaut's theorem, a proof use one variable mean value theorem.
Okay,
And
and you
question
want to
was
prove
that
it for higher dimension.
a question is that does proof uses mean value theorem for multivariable? Sorry, proof of Claire's theorem use multivariable mean value theorem. So it use one variable mean value theorem. So can we not say it use multivariable mean value theorem also because it is a special
Okay.
case?
Okay, you want to say that
Mm,
it is using the mean value theorem. So are they using the inequality or the equality? Because in high for higher dimension we have inequality, and for one variable we have equality. That's the main difference, no?
mhm. Yes.
Yeah. Also, are they using the equality part?
No, they just ask which of the following uses the mean value
No,
theorem of
in
several
the proof,
variable.
in the proof when they are using the mean value theorem, so they are using it as equality or inequality.
In the proof, mean value theorem is just one variable case, na? So that is equality form.
Equality, na? So you see, if that if taking inequality also works, then we can say that it is using that the one of multivariable. And if that equality is the strict condition, so I don't know how they are proving. So if that equality is the strict condition, in that case you cannot say that you are using the multivariable one.
Oh,
So you check that proof again. In that proof, if you can take inequality also, that also satisfies, then you can say that, yeah, the multivariable one is used. I think the main difference is that only, na, the difference of equality and
but
inequality.
equality is also there in multivariable, less than equal to, I think.
Less than equal to, na? So we cannot
So
guarantee the equality.
okay.
You see that proof, you'll get it. Okay, then.
Hmm. Okay, ma'am. Thank you, and good night.